All right. Welcome, everybody. This is the second talk by Jaco on complex topics. Let me just do the quick introduction a second time for those who did not see or participate in last week's, or in Wednesdays, I have to say, this time around. Jaco has gotten his degree originally in Stellenbosch, then went for a postdoc to the WITS, for a postdoc to UCT, and he didn't put in his short bio that he has a permanent position at UCT, which I should have guessed at.
Well, starting 1 October, so not yet. It's still in the future.
Okay, all right. But you signed something.
I have signed something. Absolutely.
Okay, right. That I consider this done and dusted, therefore. And he's going to continue with actual research topics at this point, beyond building on the introduction he gave us on Wednesday. So take it away.
Absolutely, yeah. So I'm basically going to be discussing quantum complexity as I did on Wednesday. I'll give a very brief introduction to it at the start of this, just to remind you and refresh your memories of what we're dealing with. And then I'd like to discuss two specific avenues of research that we've been interested in. First is to develop efficient algorithms to approximate or to compute curve complexity and spread complexity, and then an application related to coupled oscillators where there's a PT-symmetric phase transition and how complexity is sensitive to this. Right, so if you want to read a little bit more, they're basically based on these three papers. They're the archive numbers. They are published with Jeff Murugan, Shajid Haq, and then Paul Larby in the first, Cameron Vieta and Nitin Gupta, who just finished his PhD in the third, and with Agia Chaturvedai and Orbiton Mitra in the second. And they have postdocs in Belgium and South Korea, respectively. So just as a reminder of, I mentioned some of these briefly on Wednesday, but complexity first started as an interesting topic in the context of holographic models. There were these conjectures by Susskind. There's a very nice paper unpacking the ideas, but I go back quite a bit earlier than that, but nice paper in 2018 where I unpacks these ideas. Roughly speaking, the idea is that the growth of complexity can be related to the growth of black hole interiors. A famous example of this is the thermofield double, and I also mentioned on Wednesday. But beyond that, it has also found some applications in condensed matter physics, quantum many-body systems, where it's been used to diagnose quantum chaotic transitions, topological phase transitions, which I unfortunately won't be able to discuss today, but I'll make some comments on it in the course of the talk on why this is possible. And the way to think about it, at least in its current status, is that it supplements diagnostics, existing diagnostics like the spectral form factor, out of time ordered correlator, and the Loschmidt echo for quantum chaos. So certainly there are other quantities that are sensitive to chaos, but complexity can be applied in systems where these computations can be difficult to perform, or in the case of the spectral form factor for PT-symmetric transition, a little subtle to compute. So just as a refresher, the central question we're trying to answer is how hard is it to synthesize a desired target state? So phi t with some set of unitary operations at your disposal. So in the game, you'll have some reference state, typically a simple state. Think of this as the lab state, some set of unitary operators, and some cost function that tells you how hard some sequence of unitaries is to perform. So for example, in quantum setup where you have three discrete gates, U1, U2, U3, you can think of the complexity as counting the number of gates needed in order to take a qubit or mini qubit state from a reference state to some target state. And if it happens that two operations or two sequences of operations give you the same state, you'll choose the one with the smallest number of gates as the complexity. So it's a minimization procedure you need to perform. Now this discrete notion is closely related to quantum computational setups, where you can really think of these unitaries as gates that you put into your circuit. But as mentioned on Wednesday, we're more interested in continuous notions of complexity, such as Nielsen complexity, where you have the accessible gates to be chosen from some symmetry group. All right, so an example would be issue 1.1, where there is a group element, there's three real parameters, In general, depending on the group you're studying, there can be any group parameters parameterizing these states. The target states, the space of target states inherits the same set of coordinates as the space of unitaries. And it's essentially a manifold of coherent states that you have at your disposal, as studied by Krylov and Gilmore. On this manifold, to compute complexity, you need to define some metric. And define complexity then as the shortest distance connecting to the duties between these 2 points. This is the formulation metric, which I will be using throughout. It has a nice property that.
Sorry, is the manifold the states or is the manifold the group?
So there's a one-to-one correspondence between elements of the states, of the coherent states, and elements of the factor group. And this was shown by Coherent. So you can think of this as elements of the factor group G factoring out H, where H is the stationary subgroup associated with your reference state. So all the group elements that act in the reference state to just give you an overall phase in this case.
Not necessarily group elements if the thing is not normal, right? I mean, you always get a manifold.
Absolutely.
But you might not get a group.
True. Yes, absolutely. Absolutely. But yeah, for all purposes, I'll be focusing on state complexity primarily. So think of this as really a manifold of states. And you've obtained the states by some set of continuous unitary transformations on the reference state. And I'll make explicit choices for those unitaries. Just as an example, this issue 1 that I've written down, the manifold turns out to simply be the hyperbolic disk in this case. So you have this manifold of states parameterized by a single complex parameter, where z is less than 1. And the metric turns out simply to be the Poincare patch metric. So this is the one notion of complexity that will be relevant. The other is spread complexity. So the original idea behind spread complexity was to try and define a notion of complexity without the need to specify some set of gates, because this is an ambiguous thing. This is something that you need to specify. It's not clear what's the appropriate choice to make in all instances. But they came up with the scheme where you can just specify the Hamiltonian of the system along with the reference state and still compute complexity. And the idea is to first build a basis for all the states that you can obtain by time evolution and superposition. That's the basis of ON. Then perform a Gram-Schmidt process to obtain the Krylov basis. And now you have this basis in which you can express that that your target state is some linear combination of them. You project them onto this basis, and this basis is ordered in such a way that it's increasing the complexity. The first Krylov basis element, K0, will have complexity 0. That's the starting state. K1 will have complexity 1. K2 will have complexity 2, and so on. And this is the spread complexity of the state. Now, you may have said that, well, this is a basis-dependent thing. So I've chosen the Krylov basis. What's the reason for choosing this particular basis to do the computation? You could have chosen any basis. Pick any ordered basis. Just decree that this is the ordering of complexity, optimal complexity 0, complexity 1, 2, state, and so on. And you can define a general cost function such as that one over there. But there's an argument for why the Krylov basis is the natural choice. So it's the following. And so the Krylov basis minimizes the complexity of the time-involved reference state in early times. This was shown in this paper here by Bolas Barani and Magan and Wu. So certainly the choice of basis is arbitrary, but there is this naturalness argument within the Krylov basis. Right, so some properties that I also discussed on Wednesday is just that on the unitary transformations, the Krylov basis will just obtain the same unitary transformation, no surprises there. And the particular case that I'm going to be interested in is if the Hamiltonian is selected as an element from some symmetry algebra. So the Krylov complexity, spread complexity, can be defined for any Hamiltonian. The Nielsen complexity is always some symmetry algebra, depending on some symmetry or some group of unitaries. But now, what if you choose the Hamiltonian to also be an element of that symmetry algebra? What happens in that case? So in that case, the time evolution operator is itself a group element. And you have this very neat feature that the time evolved reference state, if you choose a coherent state as your original reference state, it will remain as a coherent state, some coherent state on the manifold as time evolves. I'll give an example of that just now. So again, go back to issue 1.1, which is a very simple example. The orbits were classified in the 76 paper by Alfaro, Fupini, and Furlow. You can write them the most general Hamiltonian you want. And the key quantity is this delta. That's a particular ratio of these couplings or relation between these couplings. If delta is positive, then you'll get elliptic orbits on the manifold. If delta is 0, parabolic orbits, and if delta is negative, you'll get hyperbolic orbits. In addition, you can compute the spread complexity for this example exactly. It's given by that, where you have the final state as some coherent state Z on the manifold. You have an initial state, coherent state Z0, and you can compute given any Hamiltonian. It actually turns out to be independent of the choice of Hamiltonian. You can compute the complexity on this manifold. It's this quantity over here that I suspect must have some geometric interpretation. We haven't cleaned that up entirely. What we have, but I'll show you a relation that we have at least clarified with that. It's quite interesting. Just to give you a picture of what's happening over here. Suppose that you start with the state at the middle. So Z is equal to 0. So you start with the state annihilated, so the vacuum annihilated by the annihilation operator. And now I can take my Hamiltonian, time evolved the state, and determine what is the time evolved coherent state as a function of time. It's always a point in the manifold. If you have gamma is equal to 1, then this corresponds to a negative delta that I showed previously. You will just get this blue orbit running off to the boundary. It's a non-compact manifold, so it runs off to infinity. If you choose gamma to be larger than that critical value, so delta is positive, you get these circular orbits, these elliptical orbits in the manifold, closed orbits, periodic in time. And if you choose that parabolic choice, so gamma is equal to 2 alpha, then you'll get something that's parabolic, sits somewhere in between the two. But for our purposes, only these two, the hyperbolic and the elliptical. Yes.
Sorry, what's on the X and Y axis here?
So this is really the, so remember that the manifold of coherent states is parameterized by a single complex parameter, Z, and Z is less than 1. So here I've parameterized that Z as an R times a radius and the angle. So think of this really as radius goes off to 1 and theta kind of all around.
So complex plane.
Exactly. So this is the complex plane. I've represented this in a particular way. Each point on that circle or inside the circle corresponds to a particular coherent state. Now this is for a particular choice. If you choose a different coherent state as your starting state, so I've now moved the starting state to lie there on the manifold. The orbits will shift, but the character of the orbits will remain unchanged. If they were elliptic before, they will stay elliptic. If they were hyperbolic before, they will stay hyperbolic, and so on. All right, so this is the picture that you get. I just want to again flash this formula. You can compute the complexity for an arbitrary coherent set in this manifold given your reference state. So the point being that as you track this time evolved state, for every point as it passes through, you have an exact formula for the spread complexity of that state as a function of time. A natural question you can ask is there a relation between Nielsen complexity and spread complexity in this special case, where you have a Hamiltonian selected from a symmetry? It's a question that you feel there must be an analytic answer for. As far as I'm aware, there's no analytic answer available. The only available answer is in the case of these rank 1 algebras, issue 1.1, issue 2, Heisenberg-Wahl, in which case we have found the following possible interpretation for it. What you can do is write on this manifold, or define on this manifold, the scalar field action, this dilaton action. Now this dilaton action has two sets of equations of motion, one coming from varying the metric and one from varying the dilaton. If you vary with respect to the dilaton, you'll just set the scalar curvature equal to a constant. And then depending on whether that constant is positive, negative, or 0, that's going to give you hyperbolic, flat, or spherical background. It's a two-dimensional manifold, so scalar curvature is all you need of the coordinate transformations to specify it completely. And if you solve for the dilaton, that's classical solutions, what you find is actually that the dilaton is proportional to the complexity, provided you specify the boundary condition that the derivative dilaton with respect to these coordinates vanish at the point z0. Physically, what does that mean? Well, that means in the context of complexity, that's your starting state. That's where it should be minimized, the scale. And as I say, it turns out that this is a linear relation. If you solve for that dilaton's classical equation of motion, you get something proportional to the spread complexity. Does a picture like this generalize to a higher rank algebras? We're not sure. We're still studying that. But as I say, it's a sort of question that you feel there should be an analytic answer for that we are trying to understand. Any questions at this stage?
If you have your closed orbits, you should get something like this page curve, right? I mean, like with entropy discussions. If you have a system where you first move away and then come back,
Absolutely,
to no entropy, right? If you have you start this with a fixed state, no entropy in that, it grows, but then it comes down again.
absolutely.
It goes because the system returns.
Yes, absolutely. So you do get these periodic orbits in complexity oscillators. Absolutely. And there will be some maximal value associated with complexity. And in this picture, it's essentially going to be what, the point along the orbit that maximizes that cost function there. So maximize for Z on that cost function, that will give you the maximal value of complexity.
So for this simple example, it's probably just the point furthest away, right?
Probably just one further away. That's also what I would guess. It makes sense. So it's the halfway point in the evolution. Most complete sense that should be the one.
I'd be interested in that one.
But that's, as I say, that's a sort of that's one question that I think is an important one to understand, because you have all these different notions of complexity. It's a highly ambiguous quantity. So you would want to resolve some of these ambiguities a little bit. So in other words, if you give me a different notion of complexity, if there's some relation between the two of them, then in effect there's only one. Then you can resolve some of that ambiguity in that process. They contain the same physical information. So that's basically what we want to try and understand. Right. Now, I just want to spend a little bit more on computing Krylov complexity and some algorithms that we have come up with to do this before I go to a specific application of it. So I just want to remind you that the Hamiltonian in the Krylov basis is tridiagonal. And this is this picture that it maps your Hamiltonian to a nearest neighbor spin chain with hopping coefficients and on-site coefficients given by these A, N, and P, and these are the Lanch's coefficients. The probability amplitudes, and this time I have corrected for the factor of N, although I think that should be phi in its conjugate. So that's probably another typo that should be, but regardless, it's closer to what we have on Wednesday for sure. So the probability amplitudes, you can compute as that, and complexity in terms of these probability amplitudes is given by this weighted sum of them. Sum of probabilities, weight them with N, and then I'll give you this spread complexity. If you go through the literature on solving these kinds of systems, what you will often see is this method over here, where what you can certainly prove is that these probabilities will satisfy these sets of equations that resemble a Schrödinger equation of the lattice. If you know the Lanch's coefficients, and I know the boundary condition is just that at time t is equal to 0, all the probability is on the 0 side of the chain, then you can solve it. And this can run into two possibilities. The first is that just numerically it becomes very difficult to compute these ones as n becomes large. If you have a system of high dimension. Now there's a large amount of error that can come into this computation solving that set of equations. The second error or second issue that's
very large is how large?
So I know that people are able to compute thousands of Lanch's coefficients, so probably tens of thousands will probably be too large, depending on the coupling limits. I have certainly seen papers with thousands of them.
Because I have seen people talk about matrix issues of this sort, and some people who are into optimizing these things
Yes, absolutely.
have claimed, okay, if you're not talking millions, it's not an issue.
Yeah.
But I have no experience with this stuff. No.
Yeah, some this numerically, I have limited experience of Zaid, who's in the work. Zaid is the guy to talk to. He's been working on that quite a bit. Some of these numerical issues. And if you know the Krylov basis should be orthogonal, there's after a while an error can build that they're no longer orthogonal. You need to re-orthogonalize all sorts of numericals. And that's if you have a finite dimensional system. If you have a bosonic system, infinite dimensional, then you're going to have to introduce some cutoff. You're going to have to cut off the system at some maximal value for n and just say, I'm not going to focus on the rest. By doing that, you've introduced some time scale where there's going to be an error that's going to start entering. Because once the probability, so let's say that you can compute it exactly, and that probability amplitude at a particular time, and that becomes non-vanishing, now that approximation breaks down. And you, as far as I know, there's no good way to approximate that error. So it's very difficult to estimate what the error is by doing that. So for this reason, in this context of systems where you have some underpinning symmetry algebra, there's another way. And that is if you can compute the return amplitude, this will give you some function in time. And you can compute the probability amplitudes not by solving the Schrödinger equation, but you can solve them recursively. And this is the formula that you can use to get them recursively, written in terms of the Nielsen coefficients. And the very nice thing about this method is that as opposed to the Schrödinger equation, where if you introduce the cutoff, you don't have a very poor way of estimating the error. Here, you can just simply sum up all the probability amplitudes you've computed and see how close it is to 1. That sums up to 1, you catch it. If it's up to 99%, you've captured a large part of the system. So that's why this is a very nice method if you have access to that. That's something that you can use. Right. All right, so that's the one algorithm that I just wanted to highlight. The second is one that I still, in some sense, in development. So we've applied it to one simple model in the process of applying this to a more involved model. But it's this question of can you perform perturbative expansions in the Krylov basis? This is really at the heart of it. So our attempt at doing something like this is the following. Suppose that you don't know the exact Krylov basis vectors, but you have a way of approximating. So you have some approximate set of Krylov basis vectors. You know, can you come up with some scheme where you can eventually converge to the correct Krylov basis by doing this? And the key thing is if you have a basis such that at order n, you're capturing part of h to the n, acting on the reference state that you've not seen before. So a component orthogonal to everything you've seen before, and that's included in your basis, the way you set it up, then this scheme is guaranteed to converge. So you have this basis, write down all vectors orthogonal to that, compute this linear combination. There's an explicit formula for the angles that you can compute, and this will eventually converge. Now, this sounds like a very hard thing to do. It's not that hard to do. That's if you have a set of ladder operators, just pick the order n of the ladder operators, for example. That'll give you this component orthogonal. Just make sure that you've formalized it appropriately. As a proof of concept, I just consider this extremely simple Hamiltonian, where you just have something quadratic in a dagger A. You know, so here I have you know, 5 different coupling constants. You can't solve for the system exactly like we did before. This exact solution is not known yet, but you can compute things numerically to any order that you want. So it's a good test. And this isn't the Krylov basis, but it's a decent guess for the Krylov basis. Take all the up-ladder operators, so a dagger, act with n powers of the model reference state, just subtract everything that's so that they give you an orthogonal basis. So that's why only powers in n and n n plus n minus 1 appear here. And then now you can start seeing, and you can get these results. So here, for example, the nitrous coefficients, the red dots there are the exact ones, and then those are the first three orders in the scheme. 0, first and second order in the scheme, and it starts approximating it. You can get some decent numerical results by looking at this. As I say, we're still in the process of applying this to a more involved system. I think this is something that
So that you couldn't get the exact, eigenvectors.
oh, it's not the eigenvector, it's the so it's not that you can't get a closed expression. So certainly you've got this Hamiltonian, you can act with it n times. It'll give you some combination of these coefficients that you now need to just orthogonalize. And you can get an exact expression for that, but there's no closed formula for arbitrary n. That makes sense. So you can get it, you can still do a lot of analytics with this. It's just that there's no closed formula for these coefficients. So that's why I said, so you can get these analytic expressions, plug in the appropriate values for the couplings, and you really have the exact value of the coefficients. So that's why it's a good testing ground for this. And this method seems to work quite nicely. Yeah, so this is just on the algorithmic side. Just so you know that there's a lot of work still that's needed to optimize the computational methods for complexity. Now, finally, let me get to an application of these ideas. So, what I'm going to consider is a model that was studied by Bender and Gianfreda in 2013, where they showed that there's a set of coupled oscillators that exhibit a PT-symmetric transition. So, the model they considered has these equations of motion. So there's one oscillator X and one oscillator Y. And you have these terms linear in the derivatives in time. So damping terms, and in the case of Y, an anti-damping term. So very crude approximation of you take these two oscillators, couple them to some mysterious external bar that feeds or that damps the one oscillator and anti-damps the other. And you can tune them in such a way that there's balance loss and gain in the system. So in other words, there will be probability conservation throughout the entire system. But you can run into issues where, even though the probability is conserved, there can be issues with the derivatives of the wave functions and those probabilities. So it's not going to be smooth necessarily. It's only smooth in very particular regions of the couplings. And if you're outside of those regions, you get this PT-symmetric transition. So in this case, you have this Hamiltonian. Hermitian with respect to the standard in the product and the Hilbert space. So PXPY, X squared, Y squared. I've just taken that var kappa as a particular combination of the couplings. And you can check that this Hamiltonian has PT-symmetry. The parity operator takes X to minus Y, Y to minus X, and similarly for the momenta. And time reversal just flips the sign of the momentum in this case. Under both of those transformations, the Hamiltonian is invariant, so it has this symmetry. What's going to happen now is that there was going to be regions of space where there will be where this symmetry will be unbroken and where it will be broken. So two distinguishing parts. And to find out where they are, a simple computation you can do, which Bender and the company do, is just to at the classical level, substitute for x is equal to e to the I lambda, so these frequencies. You get this quartic equation for the frequencies, and depending on if the solution to that is real or complex frequencies, you will have broken or unbroken PT-symmetry. You can solve for them, and the graph looks something like this, where you have these three distinct regions. Only the lightest color region in the middle there is the one where you have unbroken PT-symmetry. So you have unbroken PT-symmetry between this coupling epsilon. So epsilon is this coupling between the two oscillators. Gamma is is related to the damping parameter. So 2 gamma is the damping parameters, and var kappa is the frequency squared minus gamma squared. So, but regardless, in parameter space, these are the two equations. As long as epsilon lies between those two lines, so epsilon greater than 2 square root of kappa gamma and less than gamma squared plus kappa, the frequencies from that quantum equation are all real. You have unbroken PT-symmetry. Now, as you increase gamma, you will see that this window starts going close, smaller and smaller. So there's only a smaller choice for epsilon that will still give you real frequencies. And after it's passed some critical value, it's no longer possible to give any real frequencies. Now, how are these frequencies going to enter into our computation? Let me just maybe make one comment on why complexity here is a useful thing to determine. So, one way that you could foreseeably try to diagnose this is to study something like the spectral form. Copy the spectrum of the system. Now, in these PT-symmetric systems, there's often some similarity transformation that you can perform. Let me just take one step back. In these cases, what often happens in PT-symmetric transitions is that after you've crossed the transition point, you can still solve for eigenvalues, but the eigenfunctions can't be normalized. This is also what happens in the issue 1.1 example I showed you earlier. For the hyperbolic functions, those the spectrum is unbounded from below, and the eigenfunctions are not normalizable. So a very similar thing happens here. There are ways to circumvent that. You can introduce things like similarity transformations to regularize the wave functions at the price of complexifying the energies. But this, it's not clear that this is always possible if you have PT-symmetry. Point just being, it can be a rather subtle thing to compute the spectral form vector system. Whereas complexity here, we're not going to be computing the spectrum at all. We're not going to be worrying about whether there is a set of normalizable eigenfunctions. We're just going to study the orbits that the Hamiltonian generates in the manifold of coherent states. That will already give us enough information to deduce whether there's broken one or symmetry. The computations are very doable in this case because, again, it's a Hamiltonian that's quadratic in momenta and position. You can show that it's an element of an algebra spanned by these generators over here. And you can again get a manifold of coherent states. If you act on the vacuum, so the A and B vacuum, those are the coherent states. There's three complex parameters parameterizing the coherent states. When you time evolve it, again, it will just remain a point on this now six-dimensional manifold of coherent states, and it'll have some character to its orbits associated with. And what you can show is that for a generic choice of coherent state, the return amplitude will always be of this form, where the frequencies that you calculated classically into there, omega plus and omega minus, the coefficients CAB aren't very important for us. It's only really the frequencies that really affect the character of the orbit. Here you can see the formula for omega plus and omega minus. It'll become complex whenever you pass outside of the PT-symmetric regime. And as reference state, you can choose just a slightly more general coherent state. And now continue with the computation and see what you get. So I'm going to focus on the underdamped regime. So this is where, in the underdamped regime, what I mean is that gamma is still below that critical value of square root gamma. So you can always find some value of epsilon that you will have a PT-symmetric phase. Always in that value of gamma. And now let's see what happens as we vary epsilon, the coupling between oscillators. So here we have strong coupling. What you see here is, well, the frequencies are both complex, and you just get exponential growth of complexity. In this case, we compute it. Here we're using the method with the return amplitude, so we're generating the probabilities recursively. This is plotted for 95% of the probabilities up to time t is equal to 1. Just exponential growth in the complexity. If you're inside the region where PT-symmetry is unbroken, you get these oscillations, Rabi oscillations. Both frequencies are real, it's just a periodic function. These frequencies, here we find 99% of the probabilities captured of the first 40. And if you're outside of the region, but on the other side, so at a weak coupling, what you find is this. It's a combination of an exponentially growing profile along with oscillations. So you have one frequency that is complex and one that is real. And this is the profile that it is. So it can distinguish when you're inside the Rabi oscillation phase, and also if you're in a strongly or weakly coupled fission response. So we can, on that phase diagram, distinguish all of them. And you can play with the parameters as long as you're inside the relevant regime, all the plots that you generate orbits. And that's how you can diagnose it with computers.
Can you briefly relate these pictures to the areas in your?
Certainly, yeah. So this first picture over here will be in the strong coupled regime. So it'll be in this
Oh, here.
plot
Okay.
here. And then the weakly coupled one will be in the left-hand side, and the Rabi oscillation.
Of course,
will be
yes,
on the right-hand side. Absolutely. So,
okay.
And yeah, as you can see, all you're doing here is I never need to solve for the spectrum. I never need to deal with any of those subtleties. I just need to ask what kind of orbits are generated in the manifold states. And this you can do for any of those generated, similar to what the orthography and Furland did for C11. And it's this exercise. So there's a question.
Does this have like sort of physical implementation? Because I see that the complexity is oscillating. Does that mean that in that region, the quantum system becomes more chaotic or less chaotic?
So in this case, it'll just become periodic. In this case, so the quantum system itself is just periodic, and that's also what you're seeing in complexity. So the time of whole set itself just, eventually will return back to its original point if you wait long enough.
Okay.
How do these plots change if you're on the boundaries of the actual?
So we did investigate that. They was quite difficult to get a really distinguishing feature on the boundary. We were hopeful that at the transition point we would see something quite dramatic happen. That's you have this exponentially growing profile of oscillations. Exponentially growing profile just decreases in a rather smooth way. So you just get periodic orbits. So it's not as dramatic as we had hoped for, but yeah.
So there's no jumps, no nothing.
Doesn't look like it from our analysis, unfortunately. We were quite hoping to see some jumps. None of those, I'm afraid. But regardless, it can diagnose these transition circuits without needing to complete the spectrum systems.
Well, jumps would make it easier to say now it's happening.
Absolutely. But yeah, so I've actually I've come to the end of my talk just for today. So just a couple of key takeaways for everyone. Complexity is an ambiguous quantity. So one of the key questions is, are these different definitions related to one another? Do they contain equivalent physical information? That's one important issue. There's a question about developing efficient algorithms for computing it. In the context of symmetry groups, this is a problem where I think that there might be an analytic solution possible in general, but this is still an unsolved problem. It would be really nice to get some insight into that. Then also perturbative computations. What's coming in the way of a perturbative computation is just, you can imagine that you have a Hamiltonian. The unperturbed Hamiltonian is from some symmetry group. So now you've just got evolution of the coherent states point light. Now you add a perturbation that takes off this manifold dividing. It explores something new that it never explored before. And now it's extremely difficult to do perturbative computations or something like that. The scheme that we're thinking of, maybe this is one way to do it, there may be other ways. And yeah, as I demonstrated to you, using complexity, you can identify PT-symmetric transitions. I didn't get a chance to talk about that today, but you can also diagnose logical transitions, such as in the diagram, as well as integrable chaotic transitions. In the cases of Hamiltonians that come from some symmetry algebra, underpinning it all is really this notion of orbits on coherent states and the character of these orbits. If you're outside of those Hamiltonians, then it's not clear what the underlying reason is or how you can identify it. But certainly in these cases, it's possible. Okay, thank you for your attention.
Thank you. A lot of fun here. You already had quite a number of questions, but I guess there are more.
Go back to the orbits.
Yeah. These ones.
Yeah. So you had a
I suppose, from what you call the complexity,
That's right, yeah.
and is there a way you can just like point to a region where it is most complex? I would have thought it would be like distance furthest away from the sky.
Yeah, so I think that is correct. I haven't done the computation carefully, but I would imagine that's right. That the furthest away from it, and you'll probably get if it goes close to 1, this denominator here will diverge. So I can imagine that's accurate.
So then this is just one definition of complexity, but if you had another one, do you think you'd get that same kind of feature?
You mean if I go to a higher rank algebra and study it there, or
So here you have this definition of complexity, but couldn't you have defined it differently?
oh, I see. Yes. So if you have, so for example, that's weighting over there, an n squared as opposed to an n. I would imagine so. Yes, I would imagine that you would get very similar expressions. Yes. At least in this rank 1 case where you can compute the Krylov basis exactly. That's really the key reason why analytics are possible. So it's just the upline operator acting on the highest weight state, the lowest weight state in this case, and yeah, you can move to a different starting point just with an appropriate unitary transformation. That takes you to a different coherent state, and you can compute the Krylov basis, and they're related by unitary transformations. So that's why you can do computations at any point in the manifold. In this case.
So all the definitions of complexity are somewhat arbitrary, but they do have unifying properties with it.
I think so. I think that is correct. Yes.
You mentioned, this is a basic question, but you mentioned coupling at some point, and I was just curious, like, what is sort of coupled to each other? Is it these Krylov basis sectors?
Oh, so I think that was, yeah. So yeah, I'm just referring, to the constants appearing that Hamiltonian. So in the context of the, yeah. So for example, this Hamiltonian, I just refer to those constants as.
As coupled.
Absolutely.
At some point you were talking about the reference coherent state. I didn't really capture what that was.
Oh,
meant
yes.
for, what that was.
I should have pointed this out. So the reference coherent state here is just the one there at the top left. So you will have, so remember that all the coherent states of this manifold are parameterized by a single complex parameter. So it's the one there, the second bottom bullet. So if you act with some unitary, that give you out a state of that form, some normalization with e to the z, a dagger. And there's a condition that follows from the fact that you have a unitary that z is less than 1. But yeah, now you can choose a reference coherent state being just that one at the top.
Oh, like that.
Start at this particular z0.
Something different. Yeah, okay, sure. Yeah.
Why do you call that a U? That's not a unitary operator, right?
Oh, it's a little, it's not clear in this form I've written it. So certainly this one here is nice and unitary. This one on the left. On the right hand side, you've decomposed it into this product of exponentials using Baker-Campbell-House law. And now it's not as clear that it's unitary anymore, but there's conditions on these coefficients. So the z prime and z double prime are related to the z in a particular way to guarantee that it's unitary. So
This the second to last line.
oh, so so this is what happens here is that you've acted with this unitary. So it's some unitary. It's this guy here, and the only piece that will survive from the action is the z a dagger.
And the rest may justify.
Yes, the rest will just give you a normalization factor. Absolutely.
But just to confirm, that's not unitary, right?
Yeah. So exactly. So the operator is actually this one in the line before that. Yes, that's right. So, and that one is unitary. You act with that on the reference state, and the result is that one in the second bottom bullet.
And then usually when we think about coherent states, it's just one creation operator, not two.
Yes. So this is actually the work by Krylov here. There's a very nice archive web on it where it's generalized coherent states, but you can write them for arbitrary legal. So this is where this enters. So the one creation operator is a subclass of these ones. But you can define it for an arbitrary legal.
So is this an eigenstate of the lowering operator?
Unfortunately not. No. So that property is special only to the Heisenberg-Weyl algebra, as far as I know. And you can in general write down any generator as a differential operator acting on the coherent states, but it's not necessarily just a scaling one in this case. The reason this is useful is that you still get a resolution of the identity in terms of these. And this follows from essentially Schur's lemma. So you can prove that there's some weighted integral of the coherent states that commute with all the generators. So it must be proportional to the identity.
And just more generally, so I missed your talk on Wednesday, I'm sorry, but what's your bigger picture here?
So the bigger picture here is really, so what we're really looking for ultimately is quantities that complexity can diagnose that cannot be diagnosed by other means or difficultly by other means. So, for example, topological transitions or PT-symmetric transitions that can be difficult in some circumstances. But this is a quantity that you can compute to diagnose if that is happening in the quantum minimum system.
So how would you talk about how you'd see a phase transition normally and how you contrasting that with this?
Well, so so in the particular example I've showed, you can see the PT-symmetric transition just by studying the frequencies and even the spectrum in that case. There is a way to compute the spectrum after an appropriate regularization. But for a generic PT-symmetric system, this is difficult to do. One thing to do would be to study one of those systems where it's difficult to compute the spectrum using those techniques and study the complexity.
So here you just tested it on a case where you already
Precisely.
know where it's happening and you saw that you could also die.
Precisely.
Okay, so chaos have some understanding of we often have exponents, so I know that by some infinitesimal change in those conditions, that's going to exponentially diverge. So what is complexity? Just
So there's actually a paper by the Marsky and company. Which I should have referenced, but I can dig up the reference. The claim there is that complexity also grows exponentially, and there's a tri-inequality. So you have the MSS bound, you have the Leopold exponent, and wedged in between them is the growth of complexity. So that is the claim, that the Leopold exponent, the growth of complexity have this tri-inequality.
But what is complexity?
Oh, it's this definition that I've given. So it's great complexity in this case that they study. So so it's this quantity over here. Compute the Krylov basis, and how many Krylov basis vectors you've developed. Each of them, it's an ordered basis for the Hilbert space, and that quantity grows exponentially. It's a function of time in the case of Krylov systems.
Right, that essentially says how many of these states have you populated after a time.
Some set of states that are kind of like a basis, and how many of them I'm populating after some.
Absolutely.
And you weight the ones that are further away from where you start from more, right? That's the factor of n.
That's right. And what you can think, the picture that you can have is that the Krylov basis now gives you something like a nearest neighbor spin chain, and the complexity is the average position of the wave function profile on the chain. That's what it corresponds to.
So I have this Hamiltonian acting on a reference state. So I'm almost like time evolving a reference state.
Yeah, absolutely. So you can think of this as I don't think this has been cleared up exactly, but I suspect the picture is that it's like the notion of complexity that you had in the case of Nielsen, some sort of unitaries. You only have one unitary now, that's time evolution, and you have the possibility to take superpositions. I think with those two operations, you could probably formulate spread complexity in that operational way. But I don't think this has been cleared up exactly. But that's my suspicion.
Is there a connection to a notion of entropy in this formulation? How would you go about this?
So there is, you get a probability profile. So on this, so here you computed the mean of that probability distribution, and you can compute something like a Shannon kind of entropy with the probability amplitudes. So phi n log phi n, something like that.
Have you tried this out on these systems? What this
So
looks
it has
like?
been computed in some systems. I have not computed it in.
Because I would kind of be interested in them because there are right there are discussions of entropy.
Yeah.
And if I see a link with complexity in them, in some sense it smells like there should be.
Yeah.
Right, and there are many things known about what you see for systems that have symmetries and return and write page curves. That's the word I mentioned, right? That sort of thing. So that would be good to see. Would that be a lot of effort? Could one turn this into a student project, in other words?
I think so. Certainly for simple models, the computations are can be quite straightforward. I think so computing these return amplitudes, that's really the aim of the game. So as long as you have a system where you can compute the return amplitude by some means, even perturbatively, you can go ahead. So
you just play this in toy models that where we as a first go.
Absolutely, and from that you can extract all the probability amplitudes, and you can compute all sorts of things. That's
Let's keep that in mind.
I guess I'm still trying to sort of see the bigger picture. So I don't know how old you are, but I'm now old enough to have seen a few sort of hot trends in physics that have come and gone. And in particular, in the late 90s, early 2000s, the big deal was nonlinear dynamics of chaos, the classical realm. And it's unclear to me what we really learned from that being a hot topic. So what do you hope to learn from this in a bigger sense? And is there something that I forgot about from the 90s that was useful?
So Walt, to be honest, I think that it's a very valid criticism. I think that the field of complexity needs something that it can compute that's unique to complexity. Personally, I've not seen that yet. So in other words, something that you compute is a complexity that you cannot compute by any other means. I don't think I've seen that yet. So even something like PT-symmetric transitions, you can diagnose this in different ways. Chaotic transitions you can compute with the time or the correlator. So it's that is certainly something that's it's certainly something that's needed. So the way I got onto this was more from a holographic perspective. There was some interest in studying the complexity for primaries, and that was essentially how I stuck my feet into it. These techniques of coherent states turn out to be very useful there. It's the big problem with that is that even if you have a particular reference state, will only stay inside that multiplet. You can never, with unitaries, at least the set of unitaries we had, move outside of that multiplet. So you have no hope of generating the entire Hilbert space of states for CFT.
Yeah, but that was one of the things that was really super interesting about chaos, right? That you could have this incredibly complex behavior, you can have this exponential growth away from initial conditions, but you have these submanifold structures that you were stuck to. So that seems like it's actually something potentially interesting. But I don't know, it's still trying to, I mean, it seems like, okay, well, I have some sort of differential equations and I can kind of play around with them and characterize them a little bit, but yeah, what is it that's super interesting to you about this, right? Is this just like, is it just playing around with differential equations for you? Or?
So my PhD involved a lot of computation of these coherent states, and with the coherent states, there's a geometric formulation of quantum mechanics that was developed by Ashtikar and his students over the years, and that's really something that really gets me. So its application in complexity turns out to be extremely useful, and it's simply because you have the set of unitaries at your disposal. You're actually a reference state. That is exactly the set of coherent states. These geometric pictures of time evolution in the systems. That's really what I'm really interested in studying, and features of them.
So this is the manifold of states.
Exactly.
Yeah. More questions? Well, if not, then thank you again. And let's stay in contact about
Absolutely.
this discussion of entropy.
Absolutely.
So what's the idea of this geometric quantum mechanics?
So, the